For the last 10 years or so, there's been this one really simple and really expensive idea driving almost everything in AI. Bigger is always better. But what if that's not true anymore? What if the whole game is changing? Well, a massive shift is happening right now, and we're going to break down what it all means.
And yeah, that's really the big question, isn't it? In this massive race for AI, is bigger really always better? For a long, long time, the whole industry screamed, yes, the playbook was easy. Just get more data, throw more computers at it, add more parameters. Simple. But now, the evidence is pointing to something totally different and, frankly, way more interesting.
And I mean, this simple, expensive formula, it's been the engine for the past decade. The whole industry was convinced that just scaling up was the only reliable way to make progress. And that belief, it led to this crazy explosion in model size. And of course, the costs just went through the roof. We're talking tens, sometimes hundreds of millions of dollars just to train one of these giant models.
It really became the industry's mantra, It's this idea that Ken Thompson summed up perfectly. When in doubt, use brute force. It was later called the bitter lesson of AI by researcher Rich Sutton. And what he meant was, it was kind of frustrating, but just throwing more raw computing power at a problem always seemed to get the more clever, elegant solutions that humans came up with. And for a long time, he wasn't wrong. Brute force was king. But that whole era, it looks like it's coming to an end. We're smack in the middle of what you could call the great scaling slowdown. That nice, predictable relationship where bigger equals better, it's starting to fall apart. Hey, don't just take my word for it. Look at this. This is the proof right here. Each of those little green dots is a smaller AI model. We're talking under 13 billion parameters. The big gray bubbles, those are the giants. But look at what's happening. See how those green dots are climbing up and to the left? These smaller, nimbler models are now regularly catching up to and even beating their massive, super expensive ancestors.
Okay, let's look at a super clear example. You've got the IA 23 model, right? It's got 8 billion parameters. Then you have Bloom, this absolute behemoth with 176 billion parameters. And guess what? The little guy wins, easily. I mean, think about that for a second. A model that is less than 5% the size is actually performing better. This isn't some weird one-off thing. This is becoming the new norm.
All right, so what is going on here? Why isn't bigger better anymore? Why are we hitting this wall of diminishing returns? Well, it turns out that just scaling up creates its own set of huge problems.
And this question really gets right to the core of the whole puzzle. Get this. Researchers have found that you can take a giant, fully trained neural network and just snip away like 90% of its internal connections. And the crazy thing is, its performance barely drops. But, and this is the weird part, if you try to train that smaller 10% network from the very beginning, it just doesn't work. So, what gives? Why do you need all that extra baggage during training if you're just going to throw it away later?
Well, the answer seems to boil down to two big issues with scale. First up is just massive redundancy. A huge chunk of the model's brain, all those parameters, are basically doing the exact same job. It's like having a committee where 9 out of 10 people are just nodding along. And second, the whole learning process is super inefficient, especially when it has to deal with weird, rare stuff.
And that inefficiency really bites you when you run into something called the long tail. Just think about, say, all the words in the English language. You've got super common words like the, and, is. Those are at the head. But then you have this enormous, long tail of millions of rare words, obscure facts, and weird concepts. Well, it turns out these giant models spend almost all their time and energy just trying to memorize everything in that tail.
And Sara Hooker, who wrote one of the key papers on this, has this amazing quote that just nails it. She says that all this effort, all this compute spent memorizing the long tail, it's like building a ladder to the moon. It's just a prohibitively expensive, almost absurd way to learn. There's got to be a better way, right?
And you know what? There is. This whole slowdown in scaling, it's not the end of the road for AI progress. Not even close. In fact, it's forcing everyone to get smarter, which is making things way more interesting. A totally new AI playbook is taking shape. So what this shift really means is that instead of just having one big, dumb lever to pull, the make it bigger lever, researchers now have this whole toolkit full of clever new techniques. Progress isn't just about brute force anymore. It's about having a whole collection of smarter, more efficient ways to get the job done.
And this chart here does a great job of breaking down that new playbook. It basically shows 3 different paths forward. On one side, you still have the old-school compute-heavy approach. Yeah, you can still train bigger models on more data for longer, but in the middle, you've got compute-light methods. This is all about smarter algorithms and higher quality data.
And then on the far side, you have gradient-free approaches, and this stuff is really wild. We're talking about giving models tools like a calculator or access to a search engine. That's a huge departure from how we've built AI for the last 30 years.
So the big takeaway here is that it's just not about raw horsepower anymore. It's about working smarter. Things like being way more careful about the quality of your data, using clever new algorithms that get the models to reason step by step, or even just letting the AI use a calculator. All of these things can boost performance way more than just piling on more parameters.
And this next idea, this might be the biggest game changer of the whole bunch. See, for decades, we had to go out and find data in the real world. But now, the cost of generating high-quality synthetic data has dropped so much that we can basically create the perfect curriculum for our models. We can treat the data itself as something we can shape and optimize. It's like being able to design the perfect textbook instead of just handing the student a messy library. It lets us finally tackle that long-tail problem head-on.
So, what does all this mean? What does a future look like when it's not just a race to see who can spend the most on computer chips? Well, it's a huge shift in who gets to play the game and where the next big ideas are going to come from.
For one thing, the future of AI suddenly looks a lot more accessible. When it's not just about who has the biggest pile of GPUs, suddenly smaller labs, universities, and individual researchers can jump back in and make real contributions. It becomes less of a resource race and more of a creativity race, which is just, well, it's more interesting. Now, there is a really important note here. Even if individual models get more efficient, AI is becoming so widespread that the overall energy consumption is probably still going to go up.
And that brings me to this Alan Turing quote, which just feels perfect for this moment. We can only see a short distance ahead, but we can see plenty there that needs to be done. That old, well-worn path of just making it bigger is kind of fading away. The road ahead isn't as clear maybe, but it's packed with new and fascinating problems to solve. And as we've just talked about, there is plenty of work to do.